Hi, my name is Anders Christensen from KGSEA Math Circle, and today I'll be teaching you guys about Sangaku, the art of sacred temple geometry. So what is Sangaku? Well, Sangaku are tablets with inscriptions of geometric theorems on them, placed as offerings by mathematicians who hope to progress their math skills in Shinto shrines or Buddhist temples. You can see some examples of Sangaku at right, which usually feature some geometric figures, usually circles inscribed in other circles or other geometric figures, with some accompanying text explaining the problem or the statement. To understand just how beautiful these Sangaku are, we need to know a bit about Japanese history. So following the famous Battle of Sekigahara, the Tokugawa shogunate took control and ushered in the peaceful Edo period, which lasted over 250 years. And Japan was amidst a period of self-imposed isolation called Sakoku from the rest of the world due to chiefly religious reasons and mistrust of foreigners. Most of the Sangaku found today date back to the Edo period, and due to the Sakoku Edict of 1635, classical Japanese mathematics developed without knowledge of Western techniques and breakthroughs, such as those of Newton or Euler. Japanese mathematicians didn't have the knowledge of calculus techniques such as differentiation or integration that they could use to solve these problems, and practice geometry like the Greeks over 2,000 years ago. And I think that just goes to show how beautiful these are, because they developed isolated from Western mathematics as kind of their own isolated microcosm. So this Sangaku was produced by a 15-year-old boy, which just shows that anybody can produce these irrespective of age and class. So the problem right here, you see an equilateral triangle, and in a triangle, there are 3 green circles of radius A, 4 red circles of radius B, and 6 white circles of radius C that are all tangent to each other. If R is the radius of the outer circle, and if big R is the radius of the outer circle, and small r is the radius of the dashed circle, find C in terms of R. So we can set up a system of equations using the fact that the circles are tangent. So we get R is equal to 3b plus 4c, which is this part right here. And we can also extend this to the larger radius by adding 2b, which is the radius of the red circle. And we also get that the large radius is equal to b plus 2a, which is this part right here, which covers 1 green circle and half of the red circle. And we can also construct a parallelogram, like you see in the on the dashed line, which proves that a plus b is equal to 4b plus 2b plus 4c. So solving this system of equations, we get that b equals 2c, a equals 6c, and r equals 10c. And so the answer is c equals r over 10. This problem, I like to call it the sunflower problem, was recorded in the diary of Yamaguchi Kanzan, a traveling mathematician who chronicled the Sangaku he saw in various temples during his extensive travels. We stick pins into the position of each vertex of a regular dodecagon, as shown to the right. Then we take a string of length L equals 150 centimeters and wrap it around the pins as shown. This forms a small regular dodecagon in the center. Find the length of the side S of the small dodecagon. So we can solve this by using some basic trigonometry, and we'll find angles alpha and beta. Angle alpha, I'm going to define as the angle that these two sides make, where this is just one of the diagonal sides of the larger dodecagon, and this is side that one vertex of the larger makes with the center of the inner dodecagon. And notice how angle alpha is 1/2 of the inscribed angle between the nearest non-adjacent pins. I just mean the inscribed angle of this arc. And knowing the inscribed angle theorem, we first find that this angle is equal to 60 degrees because it's 2/12 proportion of the circumference is 2/12, so it's 60 degrees, and so we have 1/2 times 1/2 times 60 degrees gives us 15 degrees for the measure of alpha. And notice how beta is this angle right here that it makes between the perpendicular from the center of the dodecagon and also this side right here. And since beta is 1/2 of the central angle, we get that beta is equal to 30 times 1/2, which is 15 as well. Notice how we can write tangent beta as S/2a and tangent alpha as A/L/24, since L is 150 and one of these diagonal lines, there are 12 of these diagonal lines, and we're only finding half of that. So now we have this expression S equals L times tangent square, the square of tangent 15 all over 12. And with the following expression, we're like 80% of the way there, but we derive an exact form for tangent 15. Using the tangent subtraction formula, which I won't define here, which I won't prove here, but feel free to do that as an exercise. We get that tangent 15 is equal to tangent 60 minus 45, which is equal to tangent 60 minus tangent 45 all over 1 plus tangent 60 times tangent 45. You can easily prove what tangent 60 and tangent 45 are by drawing a unit circle. So I'll also skip over that part. So we get root 3 minus 1 all over 1 plus root 3, which comes out to 2 minus root 3. Plugging in L equals 150 centimeters, along with the value for tangent 15 gives us approximately this number right here. And this was actually inscribed on the original Sangaku, and the mathematician boasted that he was up to 15 digits correct. And now with modern computation methods, we can see that his boast was true and that he was actually precise, which is very impressive considering that all of the computations were performed on Japanese abaci called soroban, and they had no access to the methods we do today. I hope that wasn't too difficult. This is the last problem I have for you today. And in the problem, triangle ABC is isosceles with AB is equal to BC. And if one chooses D on AB and J on CD such that AJ and CD are perpendicular, and the incircles of triangle AJC, ADJ, and BCD all have radius R, then prove that R is AJ over 4. So this one is kind of the hardest problem I have for you today. It's still not too difficult with the right thinking. So those of you at home, if you want to solve it, go ahead. I'm just gonna show the solution. Since the incircles of triangles AJC, AJD are symmetric relative to AJ, notice how the same holds for AC and AD, and hence AC and AD are equal to A, and CJ and JD are equal to C. We'll just call those two sides A and C. If AJ is equal to D, and DB is equal to B, then BC can be expressed as A plus B, since it's isosceles. And from triangle CDB, using the incircle area theorem, then we get R is equal to 2 times the area of CDB over CD plus DB plus BA, which is the perimeter. And that can be simplified as the area of CDB over A over 2 plus B plus C. Repeating the same thing with CAJ, we get that R is equal to twice the area of CAJ over A plus C plus D. And that can be simplified as the area of CAD over A plus C plus D. Hence, B over A is equal to CDB over CAD, which is equal to A over 2 plus B plus C over A plus C plus D. And since we're finding B over A, we can be simplified to A over 2 plus C over C plus D. From B over A equals A over 2 plus C over C plus D, from which B equals A times A plus 2C over 2 times C plus D. We can apply Stewart's theorem here, which I won't prove, but you can do that as an exercise using Pythagoras. That gives us CA squared times DB plus CB squared times AD is equal to CD squared times AB plus AD times DB times AB, which is quite a mouthful, but you can write it as this number, right? This expression right here, using our variables. And from that, we get B is equal to A times 4C squared minus A squared over 2 times A squared minus C squared. From the two equations we found for B, we first note that A squared minus 2C squared cannot equal 0, as that would make the expression undefined. And we find an expression for C plus D as A squared minus 2C squared over 2C minus A. Notice how applying the Pythagorean theorem in triangle CAJ gives A squared minus C squared as equal to D squared, such that A squared minus 2C squared equals D plus C times D minus C, applying the difference of squares. And so we have A squared minus DC squared, 2C squared equals A squared minus 2C squared over 2C minus A times A squared plus 2AC minus 6C squared over 2C minus A. And notice how this part is just this expression minus 2C. And this implies that 3A equals 5C, or A equals 5X, C equals 3X, and D equals 4X. If you're not convinced, try just proving that this thing here, where we multiply 2C minus A twice in the base, is equal to 1. And you'll get that A and C are in the ratio of 5 to 3. And so since A equals C minus R plus D minus R, we get R equals X equals D over 4, which proves that AJ over 4 is the radius. So I hope that problem wasn't too difficult. And that's about it. Thank you for listening. I think geometry is great. I was inspired by the whole Japanese theme, so I composed a haiku. With geometry, one captures the universe on an empty page. Thank you for listening.